This video will outline the steps that can be taken to prepare data for audification, and will discuss key considerations at each step. There's no need to take notes, as this information is also available in a PDF document which can be downloaded at the link provided below. After watching this video, you should have a basic understanding of how to select a dataset that is appropriate for audification, how to handle any bad or missing values, and how to scale the data to the appropriate range for creating an audio file. Remember, the ultimate goal in this approach is to then listen through the resulting audio to extract subtle features that might elude visual detection. First things first, the data that ideally lend themselves for spectral analysis through audification are one-dimensional time series, and when working with multiple data parameters, it is usually preferable to write each as an individual audio file. It is also important to have data with observations that are recorded at equal temporal intervals, as even a slight change in the sampling interval can produce noticeable artifacts in the spectrum of the resulting audio. A large source of available data is also preferable, and this is due to the extremely high sampling rates that are used when playing back digital audio. 44,100 data samples are equivalent to 1 second of audio at the standard rate of sound file playback, that is to say, the sampling rate of CD quality audio. This means that we can auditorily assess 1 million data samples in approximately 23 seconds. Now let's look at how to turn a time series into an audio file, including the treatment of bad or missing data. Here we have a hypothetical dataset, with time progressing from left to right along the x-axis and arbitrary values along the y-axis. You'll notice that this plot is non-continuous, that is to say, there's a single missing data value. Almost any data you encounter will have a certain percentage of bad or missing data values, and these values need to be cleaned such that artifacts in the resulting audified data are minimized. These artifacts will generally manifest as clicks and pops, and can be quite distracting while listening through the resulting audio. In this tutorial, we'll cover 3 data cleaning methods. The first, and recommended method for filling in missing data values, is linear interpolation, which involves drawing a line between the nearest 2 data values and reconstructing the missing data as points along this line. So long as the data gaps are not exceedingly long, this process will smooth them out such that audible clicks and pops are minimized, and the duration of the resulting time series will not be affected. A second approach involves assigning each bad or missing data point a predetermined value. 3 hypothetical values are shown here, and we can see that while it's possible to reproduce a relatively smooth curve, assigning a predetermined value that falls far from the mean can produce sudden changes that will produce artifacts in the audio. One form of interpolation resolves this issue by assigning bad or missing data entries the same value as the nearest known data value. This nearest neighbor interpolation is preferable to arbitrary value assignment, but can still produce audible artifacts when the jump from one data value to the next is sufficiently large. A third approach to data cleaning involves the exclusion of bad or missing values. That is to say, we remove these values from the data altogether. While this method may be tempting, it should generally be avoided, as the overall length of the resulting dataset will be shortened, and the temporal progression of the audified data will no longer match the original rate of data collection. While listening through the audified data, it may be difficult to know where these bad or missing values occurred, and it will be impossible to know how large the data gaps were. It is for these reasons that linear interpolation is the recommended method for handling data gaps, as clicks and pops will be minimized, and the overall length of the resulting dataset will be preserved. This table provides an overview of the data cleaning methods discussed in this tutorial, and is included in the PDF document. It should be noted that in many cases, extreme outlying data values should be flagged for data cleaning, as they can greatly reduce the dynamic range of the resulting audio once the data has been scaled to the appropriate range for sound file playback. Now that we've discussed how to clean the data, we'll review the basic concepts of the scaling process. This interval spans roughly 4,000 data samples from solar wind magnetic field measurements gathered by the WIND spacecraft on the 19th of November 2007. What we are observing here is the passing of an interplanetary shock. Appropriate scaling will maximize the signal-to-noise ratio of the audio signal while simultaneously avoiding clipped values. The range to which the data values should be scaled will vary based on the bit depth of the audio, the file format, and the platform used for audification. For audification in IDL, we find the maximum and minimum data values in our vector and scale the entire dataset such that these values fall between 32,767 and negative 32,768. The resulting data are now the appropriate format to be written directly to an audio file. Here we see the resulting audio waveform in isotope Rx. Note that as the original data spanned only 4,000 samples, the resulting audio will be less than 1/10 of a second in duration at the standard rate of sound file playback. We can begin to hear what sounds like a sort of knocking event, but the example goes by too quickly for our ears to fully appreciate the evolving frequency spectrum. This is why it's important to draw from a large source of available data. When we expand the playback region to include the surrounding 149,000 data samples, we can place this transient percussive event within a larger context. This tutorial covered the basics of how to select an appropriate dataset and prepare it for audification. Feel free to go back and review any portion of the material at this time. In the next video, we'll step through the audification process in IDL.